Some advantages in life do not arrive fully formed in adulthood. They begin as microscopic variances in early childhood, gathering compounding momentum with every passing year until one individual outpaces their exact peers. In labor economics, one of the most consistently documented of these advantages is physical attractiveness. Decades of data show that better-looking people earn a measurable wage premium over their careers. This line represents the accepted baseline for this phenomenon. A 1 standard deviation increase in physical looks historically correlates to roughly a 7% boost in lifetime earnings. The standard professional assumption has been that this premium is a late-stage labor market dynamic. Economists typically attribute the gap to employers discriminating during the hiring process, or customers demonstrating a preference for attractive staff. But observing an earnings gap at age 30 does not explain its source. We have to ask whether this disparity truly originates at the interview table, or if it is built into the pipeline decades earlier. A 2019 National Bureau of Economic Research working paper by Daniel Hammermish, Rachel Gordon, and Robert Krosnow reevaluates the origins of this wage gap. To find the root of the disparity, their data shifts the focus away from adult employment and back toward primary education. The beauty premium begins long before the first job interview. It originates early in life as a gap in human capital. The magnitude of the finding points to a specific source. Up to 80% of the economic return to beauty originates from a compounding advantage in early cognitive development. To accurately understand adult wage disparity, economists must evaluate the beauty premium as an issue of childhood cognitive value added. The researchers utilized the U.S. study of early childcare and youth development. This longitudinal study tracked a panel of over 1,300 children across 11 distinct chronological waypoints, from 6 months old up to 15 years. To establish the independent variable, beauty, the researchers extracted thin slice video samples of the children at each age. Groups of undergraduate coders then rated the overall attractiveness of the subjects on a normalized scale. The methodology was tightly controlled. Audio was muted to prevent personality bias from influencing the coders, and the resulting visual ratings achieved a high internal consistency with a Cronbach's alpha of 0.88. The dependent variable here was cognitive achievement. This was measured through objective, age-appropriate standardized metrics, like the Woodcock-Johnson Applied Problems math tests, administered repeatedly as the children grew. This equation is the mathematical engine of the paper. It is an autoregression formula designed to isolate exactly how a child's looks impact their academic trajectory. The S'(T-1) term controls for the student's previous test score. By anchoring to past performance, the model measures the specific educational gains between waves rather than attempting to capture a raw baseline of intelligence. The alpha term is the coefficient of interest. It represents the isolated impact of beauty at a previous wave on the subsequent change in cognitive achievement. Running the data through this model reveals that a 1 standard deviation increase in average beauty raises subsequent objective learning outcomes by approximately 0.04 standard deviations per wave. Because this value is added between every testing wave, the advantage compounds. The attractive student is gathering academic mass year over year. By the end of primary school, better-looking children have already accrued a statistically significant and compounding cognitive advantage over their peers. This results in a rigorous economic question. Are we actually measuring physical attractiveness, or are we simply measuring wealth, race, and parental education masquerading as good looks? This tall column represents the raw baseline effect of beauty driving test scores before any socioeconomic controls are applied to the model. Using a Gelbach decomposition, the researchers introduced the gamma X vector to control for race, family income at birth, and parental education. These demographic controls do shrink the overall effect size. However, a statistically significant beauty effect remains independent of class or race. This leads to the question of reverse causality. Is it possible that scoring well on a cognitive test makes a child appear more attractive to outside observers? To solve this, the researchers used an instrumental variable approach. They evaluated the looks of the mothers and then instrumented the child's looks using the mother's looks to isolate the exogenous variation in physical appearance. The IV check reinforced the initial model. Filtering the data through the mother's appearance yielded even stronger impacts on the child's value-added test scores. The cognitive gap is a durable effect of physical appearance, rather than a statistical artifact. If better-looking students learn faster, we have to identify the mechanism. What is actually happening inside the classroom to drive this human capital acquisition? There are 3 common hypotheses used to explain how lookism might operate in schools. The first is the halo effect. This suggests teachers feel closer to attractive students and unconsciously invest more pedagogical effort into their success. The second hypothesis focuses on social friction. It suggests less attractive children face higher rates of bullying, which reduces the mental bandwidth they can dedicate to learning. The third hypothesis relies on internal psychology. Attractive children receive constant positive reinforcement, leading to higher self-confidence, which then translates into better test performance. The researchers tested these assumptions by modifying the autoregressions to introduce specific proxies for teacher closeness, reported bullying, and measured student self-confidence. Controlling for all 3 of these proxies barely absorbs the beauty coefficient. While these factors relate to a student's experience, including them in the math decreases the beauty effect by less than 10%. These standard behavioral assumptions do not adequately explain why attractive students learn faster. The exact interaction occurring between the child, the teacher, and the environment remains difficult to isolate within the data. While the exact psychological mechanism remains a black box, the structural advantage in human capital acquisition is evident in the longitudinal data. To trace how this early advantage fully matures, the researchers shifted their focus to the UK National Child Development Survey. This dataset tracks a cohort from age 7 all the way to age 33. This shift allows us to mathematically separate the direct effect of beauty on earnings from the indirect effect that operates through the school system. They structured the UK data into a triangular estimation model to isolate these pathways. First, the model maps the cognitive baseline. A 1 standard deviation difference in looks generates significantly higher reading and math scores by age 16. Second, the model connects those scores to attainment. These higher test scores translate into 0.4 additional years of total schooling. Finally, we contrast the indirect human capital path against the direct labor market path. In adult earnings at age 33, the overall impact is roughly 4.5% higher wages per standard deviation of beauty. The data isolates the primary pathway. Between 20 and 80% of this wage premium flows through the indirect educational pipeline, rather than hiring bias. This does not mean the schooling itself is unproductive. It indicates that the benefits of schooling are tilted toward better-looking students. The beauty premium extends far beyond the hiring desk. It is a compounding, lifelong